So today we get the actual formula for Stoffel-Fields, and then we can do something more with that. Okay, so what did we do last time? We talked about our ds squared. Okay, what did we say that equals?
Not minus c.
I agree, not that. Generically, it's always making me cry.
It's a song.
G.
Yeah. G.
G.
You knew.
Thank you.
X.
D. X.
dx.
Dx.
Oh no. Dx alpha.
Oh,
Yeah.
I have to kill you. Which kidney do you want me to move with my bare hand? Okay. U. D.
X new.
Thank you. If you said beta, that would do it. That's just no, I'm sorry. Okay, we have that. And what we want to do is we want to integrate along the world line. So I took the square root of this. And then we're going to integrate this along the world line from some I'll say like S initial to S final here. So this is equal to S. And this we had to figure out what to integrate on, and what parameter did we say we're going to integrate on?
Tau.
Tau. So we multiply the top and bottom here by a tau. Took the one tau in here, making it a tau squared. More like this, and so we're going to integrate this from some tau initial to some tau final. So our picture is this: is that here's going to be our S initial, here's our S final, like this. As we integrate along here, at any given point here, this is the point tau. So this is basically our tau initial here. This is our tau final. This, so the tau's anywhere along here like that. This is our world line. And we want the geodescics from this. And we said the geodescics occur when we said if we looked at a variation in this, so this is a variation. Oh, that's still there. This is a variation in this. It's just like a D, but it's variation. This equals zero. And what we're going to do, we're always going to assume, we're going to basically assume that the delta S at T initial and the delta S at T final equals 0. So we're going to look at paths like this. This is one. This is one. We're not going to be one that starts here and go like that, because we're going to assume that all the variations in S are 0 at the endpoints. Okay. And so this is exactly like basically Hamilton's principle that we did in custom mechanics. Okay. And so what we want to do is do that. So is it okay if I erase this line here and start the equation here? So we can start this. We can say that this ds is going to be put this in front. We'll say this not that at all. Here, this until initial, not final. I'll just write this as a square root from the logic tau. And then that's the same thing as initial, final. What did we say that is? Well, the whole thing is equal. If you take the variation of the square root, what did we say that was? Remember this whole thing here. This is the variation on something here we can look at. Okay, so that gives us
Minus, or no, 1/2.
so we get the 1/2 here
Then delta, or just the thing.
over that square root,
Yeah.
right? Because what are you getting? You're going to put on the 1/2, and you're going to get that from the minus 1/2. And now you have to take the variation on all the terms in this square root. There's 3 of the terms. So we have a triple product. So we have the variation on G mu nu dx mu d tau. Dx mu d tau. Plus G mu nu. And then what we're
The variation in dx mu d tau.
yeah, so this is variation in dx mu d tau. Dx mu d tau. Likewise, the same thing in the last term. So we'll switch your product.
What's the difference between a variation and a derivative?
Oh, mathematically, they're going to be the same, but a variation, if you remember from classical mechanics, they're basically going to be something consistent with any constraints in the system. They don't have to be necessarily displacements. You can just treat them as like a D. Just it's like a B.
Yeah.
Okay, now what we can do with this term here. I can write this as D delta mu d tau. I can write this term here is D delta nu d tau. And what did we say we could write this term as? Maybe we didn't. So imagine this is a D. I want the differential on the G's. The G's are a function of the X's. How do you write that?
Delta G, delta.
Partial. So partial G mu nu with respect to X, let's say sigma. Delta X sigma. Okay. And what I like to do is actually pull a delta X sigma out of here, delta X sigma out of here, and then put these all over here. And then what's the argument from classical mechanics? What do you know about all the X's here? The X's here are independent variables. So if I pull out a delta sigma out of here, this always equals 0. I haven't specified the path of it. What could we then conclude?
Path independent.
No? All the terms in the interior here of the incorrect are actually 0. Okay. That's ultimately where we want this one to head. Okay, I'm seeing a lot of blank books. So people say, what the hell is going on in this class? Ask me later. Ask your question.
Can you just say that again?
Okay, so this is preview. Okay. We will rewrite this expression as the integral here, stuff, okay, delta X sigma, delta tau equals 0. Okay, we're not there yet. This one's already here. It's my delta X sigma. That's great. This one isn't quite like that. This one isn't quite like that. We're going to do that. We're going to pull that out of each of the terms. And these are independent variations. The next segment. So it doesn't matter what variation I put in here, I always get 0. And the only way that can be the case is if this entire argument equals 0. Okay. So that's ultimately what we're going to try to do. Okay. Now let's want to deal with this term in front here. So before we do this, okay, are there other questions?
That's a delta X mu, right?
Oh, you see me do something like this is stupid. Call me on it. So what do we have? So before we do this, let's rewrite This one. Yeah, so what do we know about this? Know that this term right here. You know that that term into the 1/2 power. This is really this G mu nu. Dx mu d tau. Dx nu d tau. Right? Well, what is this? That's the definition of u mu.
Oh, yeah.
Right? That's our forward velocity. And this is a definition of u nu. And here's G mu nu. Okay. So that's the same thing as u mu. Now, what kind of quantity is this?
Scale.
Is a scalar under a general coordinate transformation. Okay. What I can do is I can switch to basically a point where this is locally flat. So in a locally flat string, u mu is what? This is going to be basically, what did that become? Like this is u0. Well, let's actually just go through this. And frame, this becomes, I guess I'm gonna have to,
No one here releases.
no, I know. Yeah. Okay, u mu. Okay, what was this? See gamma?
Let's see why
Gamma Vx. Or Ux, depending which way you want to write it. Vx, Vy, gamma Vz. Okay. So u mu is what?
everything squared with the first term, and there's a negative.
Exactly. So this is minus gamma squared c squared plus gamma squared vx squared plus gamma squared vy squared. It's gamma squared vz squared. You pull out the gamma squared. Pull out a minus gamma squared and a c squared. What does that leave me with?
No. Wait. What's
Hey, what is this term?
1.
Thank you. Okay. Minus the next term.
V over C squared.
Vx squared over c squared. Minus Vy squared over c squared. Minus Vz squared over c squared. Does this have another name?
Probably V.
I can pull the c squared, and this is Vx squared, this is Vy squared, this is Vz squared, which is
Or V vector.
minus V squared over c squared.
Oh, yeah.
So what I'm off to minus gamma squared c squared all times 1 minus V squared over c squared.
I do have a question. So the lower index is a covariant.
Correct.
Why are we dealing with a covariant right now? Because like in the G mu
I use this combination here. Oh, which one did I do? I did this guy. I can use that to know this. So this guy here, this is G mu nu.
Oh,
Gx nu.
all right, that's it.
G tau. And U tau.
Thank you.
Yep. Is this a name?
1 over gamma squared.
This is 1 over gamma squared. Okay, so this is minus c squared, frequently known as a constant. So what can I do with that piece? Get rid of it. There's us. So I can rewrite this. So the here terms of the minus 1/2 power can be 4. And divide it out. What that leaves is you're gonna go from tau initial to tau final. Oh. Big bracket. Partial G mu nu X sigma. Sigma plus G mu nu dx mu d tau dx mu plus G mu nu dx mu d tau d gamma x mu d tau d tau. Not all we can zero. We basically got rid of the sum factor here. This is the minus 1 over c squared term. I just cut it away. That makes sense? Do we continue the quest? Yes. Dragons exist to be slayed. That's what they exist. Okay, so how are we going to do this? We're going to basically have this piece and this piece. We'll use. What's everyone's favorite integration technique?
Integration by form.
Integration by parts. Use integration.
Thanks very much, fun.
The parts. It's the most common one you use in physics. Yeah. You have an integral, you don't know what to do with that integration. So let's do this one here. So over here, we have this guy here. So look at the second term. Let u equal something, and dv equals something. Well, we're going to let u equal to g mu nu dx nu d tau. And then dv is going to be everything else. D delta x mu d tau d tau. Okay, what would I have to take the tau derivative of to give me this term? Don't overthink it.
It will be delta x mu t.
Just mu. It just be this delta x mu.
Mm.
Right.
Oh,
I take the time derivative of this and get this.
oh,
And what does this term give me? This du. This is in the time derivative of this piece. Does that make sense? Good. Okay, so now what do we do with this? This integral then is this times this evaluated at the influence. That's a set G. minus the integral of the other piece, minus the integral of this. As the French say, oui.
Yes, indeed.
It's the, right?
What?
Never mind.
Oh, there's two of them. It's this guy times this guy, so it'll have the delta, it's new. Thank you.
Yeah, that's what I was.
It's about this guy here. Now, as the French say, oui.
Again.
They have a word for everything.
Yes. I know. It's
Crazy. Sounds like it's a language.
yeah,
Now what happens here? What do you know about the delta x mu at the initial, the final?
the other constant is 0.
One of those statements is correct.
It's
It's 0. We're assuming no variation at the endpoints. Right? So we're assuming that these guys here, delta x mu, the initial, the delta x mu, the final, is a 0. No variations at the endpoint. So we don't have to do this piece here. So likewise, this integral here, the third one, likewise, the third element. This guy. Does that equal? Minus integral from the initial to final.
D over D tau.
Oh, let me zero. Now, this guy here, dx mu d tau times delta x nu d tau. So what I'm going to do is I'm going to basically erase this line here, and I'm going to basically write the line below this. Is that okay? Try to shift those stuff. So the 0 equals integral from t initial to final. Partial g x g mu nu, partial x sigma, dx sigma, minus my buddy right here, and I put up the integral, so d by d tau of. Okay, make sure I don't make any mistakes with this, because this is, we're gonna have a, there's a very delicate dance in the industries, indices that occur. And if the indices don't dance, you got a daily homework problem. You. I'm gonna pull up the detail and everything. Then I have the. Does that make sense? Does that make everyone agree? Now, what did we want to pull out? I want to pull out a partial x sigma. Here's a partial x mu, and here's a partial x nu. You are pros of this, you tell me what we do.
Just write partial x sigma and try to cancel things out.
We have to do something here.
Okay.
We're summing on the mu's here. So it's a dummy index, doesn't matter what index I have. So I'm gonna replace, in this case here, I'm gonna replace mu with sigma. Listen over here, what do I do?
Placing you with.
Oh, yell at me, this would be bad. This is a mu, this is a,
No.
You just switch them.
no, I think I got these switched. This one here is a mu,
Yeah.
this one here's the mu. Everyone see how I screwed that up? Oh, this was new, this is new,
Yeah.
this is new.
Well,
This one here is, no, I'm fine.
yeah.
Good, never mind. U goes to sigma here. So what's gonna happen over here?
New. Goes to
To
sigma.
summing in the mu's and then the new stuff. Let's say it's the new. Let's just see. And then I can factor out the delta x sigma. So I can now rewrite this. 0 equals the integral from tau initial to tau final of partial g mu nu partial x sigma minus d by d tau g sigma nu d x nu d tau minus d by d tau of g nu sigma dx mu d tau. Big bracket delta x nu. So delta x sigma of tau. Does that make sense? Everyone agree?
Yes.
Now, what's the argument here? These are delta x sigma are independent variations. It doesn't matter what they are. Ergo, so I'm going to use line. Ergo, the integrand
Is a constant.
particular constant
Yeah.
0. Right? Because this always equals 0. And so the only way to have this to be the case is if the integrand itself is 0. So what we're left with finally, well, we're not, there's no final to it. Again, this is a question. Therefore, that's too strong, but it implies finality. We're not done. Do I believe what I have written? I think I do. Okay. Now what?
We can find it, so we have.
We remove the integral. The integral's done.
Oh. Well, now
We
we.
equated the integrand to 0.
Whoa.
Oh, really? Ooh.
We have to pull out. No.
Okay, what does this smell like?
They're looking at it.
Time. Product. This is a problem that never ends. It's on. What's the next term? G sigma nu.
Oh, it's second gear.
Second row. Sigma minus 50T. And tau. And likewise for this guy. Okay. We ain't done. I'm gonna write that. Oh, damn it.
Yeah.
What's the two terms on here that I dropped? There's a dx mu d tau, dx mu d tau that I dropped in the term. Oof. Remember? Go. This is early on. Let's go back. We had this derivative here, this guy, right? D tau. And that gave us this 1/2 square root here. And then we had a triple product rule here. We had this partial, we had this d g mu nu dx mu tau dx nu tau. And then the other two terms, and then this term here we wrote as this. I dropped these two terms here. I apologize. Did that where I made that up mistake? Go back and fix that, so I won't go on to get that fixed.
No.
Go.
I mean, it just died on me, so that's why I switched to paper.
You see what I messed up?
Yeah, this, well, it's,
So
yeah,
it's dropped here,
yeah, I think back here.
dropped, I think it's, yeah, it goes right back to,
Or yeah, maybe.
so I have it there.
Yeah, that was last class.
So if you look, it's basically, I show you why that one term is equal to minus c squared. And then I drop it here, so it actually just, it goes in this guy. So, I think, now this is what I'm gonna beat up. So if you look here, we have this delta G, which is this guy here. And I dropped those two terms. Here we have. So we go to here, it's right, it's written for here. There's a dx mu d tau times a dx mu d tau. Did you find that, Jake?
Yeah.
Okay. So I'm gonna put this in here, right?
You are at the limit of the phantom zone.
I am. It's there though, that works, but it is at the one. Not care for general Zago, no, it is general Zago. Okay, let me know when you have that patched up. See, that might happen if I were doing a big black room, but not blackboards, just a head call there. Let's foresee. Okay. Let's beat on this guy. How can I write that? We're gonna use the rainbow. This is gonna be partial G sigma nu with respect to
X.
X, let's say beta.
Is that it?
That's not mu, sorry. Mu.
And after that, well, from
E
X
X
mu
U
over dt.
D detail.
Now,
Tell me what I'm gonna do with this term here.
the same as that. But
This is gonna become partial of G mu sigma with respect to
X mu
X nu.
d X nu beta.
Okay, so now we're gonna rewrite it. So I'm gonna put these two terms on one side, all the other terms on there. Okay, so I'll start off with this term and then this term. This term. Then I have this term. That comes into the minus. Then this.
Oh my god.
Okay, we're actually in good shape. I'm thinking around mistakes. Now, if there are, you have a hell of a deal of homeworks. Okay. Now, what can I do to this term, and this term, and this
Thanks.
term? I can factor out the dx mu dx nu. I'm going to factor out that. Now, these terms here, what do they do? They look. I'm summing on nu here. I'm summing on mu here. And remember, this is symmetric in the index.
Then they're the same.
They're the same term. So this I can write as 2g sigma nu d squared dx nu d tau squared, okay, plus bracket partial g mu x sigma minus partial g sigma nu x mu minus partial g mu sigma x nu dx mu d tau dx mu d tau equals 0. I was almost over. And divide through by this minus 2 here. So I'm gonna distribute for the minus side. So these are going to be positive. It's going to negative. I wrote this one first, so you don't have to, and I wrote this. I should probably.
There's a G mu mu. Should be mu sig. No. Wait, what?
This guy comes from the minus sign there. Multiply everything through by minus two. Divide everything through by minus two, so this becomes under the minus sign. That goes here, so this thing goes here.
Did those two?
Oh, they dropped, sorry.
Then oh, you wrote that one first.
Yep. For no reason.
Oh, I see. Yeah, I guess. Yeah. Okay.
I should have probably actually switched them to those.
Oh, but yes.
Okay. Now tell me how to get rid of this guy here. We know that if I multiply this by G, it's a Q. If I have G beta sigma, G sigma nu, what does that equal? That'll always give me my delta. And multiply this by here. If I do that. Do this. Mind if I just do that? Actually, I should keep my brackets the same. Mind if I just do that?
Is that supposed to be a minus?
Which one?
And
Sure.
the other one?
These are plus.
That-
And then you just
They were what?
sorry. Because you saw the things on the outside.
Oh, that's supposed to entail everything.
Okay.
I guess it's not consistent. But
I mean, it's
no, it's not consistent. Okay. Now this guy goes to delta beta nu. Dx nu here like this. Plus 0. What does that give me? This gives me d squared x beta. D tau squared plus 1/2 g beta sigma times it's partial g u sigma dx nu. It's partial g u sigma dx mu minus partial this protects sigma g nu dx mu d tau dx mu d tau. That is one of the most famous equations in general relativity. And recall this whole thing here. That whole thing here is by definition microsurface. It's beta mu nu. And this right here, gamma is symmetric. From the lower indices. Well, this is the same as this. This is called the geodescic. We want to find out how something is going to move in our curved space. There's no forces acting on it. It's going to follow the geodesic. That's the equation we're going to have. We are going to be solving that equation a lot. Turns out that equation is straight from hell. It's going to hurt. It has an edge. All the equations in general relativity have edges. Very, very sharp, dangerous edges. Okay, let's calculate a Christoffel symbol for something simple. I'm going to show you another way to get this, and it's going to be based on metric compatibility. Well, let's do an example first so you can actually see how this puppy works. Okay, so the one example we're going to beat to death is a two-sphere. That'll be our first non-trivial example of a curved space. So let's calculate the gammas for a sphere radius r. So what would be the coordinates we'd have for this? If we're a bug and looked on that sphere, what would be our coordinates?
X, Y, Z.
No.
The angular ones?
Yeah, our coordinates would be theta and
B.
B. So let's write ds squared. If she looked on this, if she looked on that. So you tell me how to do this. So if I'm here, I keep phi fixed. Again, phi, these are the same thing. Okay, I'll probably have anything between the two. So here's your theta. Here's your theta. I'm going to come over to here. So here's my d theta. So what is my ds here?
RD theta.
That's just RD theta. Okay. Now, I'm going to keep theta fixed. And vary phi. What is this? This is going to be come up here. This distance here is r sin of theta. Look at that projection in the xy plane. Here's my phi. Come up here like this. So this side here, but this is to be phi. What is this ds? So the radius is r sin theta. So r sin of theta. Phi. So ds squared is going to be what? It's going to be that squared plus that squared. So I get this. This case here, what is my G mu now? I would write it as a matrix. Now this has to equal G mu nu dx mu dx mu.
It would like R squared.
Now, so the 1, 1 coordinate The dx1 is going to be d theta, and the dx2 is going to be d phi. So what is this going to be? R11 is what?
R squared.
R squared. Is there any term that has a d theta d phi? In that? No, so these are 0. This one corresponds to?
R squared sine squared theta.
This is R squared. Sine squared theta. So this is my G. So using this G here, what I want to do is calculate all the non-zero Christopherson. Okay. That'll be tomorrow. And then I want to show you with metric compatibility, how we can actually make use of this. Make use of that and actually drive the Christoffel symbols a lot easier. With one piece of price, it was a price that does have to be paid. But it's something we're gonna use a lot of. Okay. We don't know how to take the derivative of a second rate tensor yet, or a third rate tensor that we're fourth rate tensor. That'll be revealed tomorrow. Okay, have a good day.
Is that derivation gonna be on the first test?
Second test.
When is the first slide?
Next week.
Yeah, that too.